Okay, in this recording, I'm going to introduce how to do reactive part compensation. So this is part one of it. Okay, let's get started. So first, we, as we do before, we clear the workspace. Just run selection. So we clear this workspace, we clear the command window, and then we set up the RMS value, and then give the voltage and the initial angle and frequency, and then omega. So next, we're going to write down the phasor representation of voltage. Okay. So by doing that, when we will use V equals to V RMS times cosine degree to radians V angle and plus 1J. So this will give this next value complex, the imaginary part of a complex number, sine degree to radian V angle. So this would be our real part. This will be our the imaginary part of it. Okay, so this is the phasor representation, but this is the voltage in rectangular representation of it. Okay, let's just print them out so we can use this command. Oops. Copy them twice. So fprintf is the command you can print either this variable to file or just print them to the screen. So I can write a text here, which in this parenthesis, and then these are the texts, and then the this will be the variable, how you want to output this variable. So I'm just going to output them by float. So this plus will give us the plus sign. So let's run this, you will see what I meant. So you can see that when I run this command, then it'll print out that this sentence, voltage in the rectangular form is, this is the variable 1, it's the real part of B. So that's 120 degree. And then the imaginary part of it. But since we need to plot out this plus sign here, this plus sign, and then the J after this imaginary part. So that's why we use plus, and then the float number, and then oops, and then J. Okay, so that's how we print out the result in a screen. Okay, so next we can do is we can let's do method 1, where we know the current. So when current is known, let's say IRMS equals to say 10 amps. Okay, the angle equals to minus 30 degree again, and then we can do I equal similar to here. So you basically can just copy everything over, but change the B to I. Okay, change the B to I. So this will be I angle, change the B to I. Okay, so I can also copy this part over. So this will be current. So this will be I, and this will be I. So let's see, if we do that, then this means that I give you the voltage and then I give you current. Okay, so if I do that, you can see that I'm sorry, run that again. Yeah, this is I give you the voltage in complex number, and then the current in the complex number format. Okay, so if I know these, I basically can calculate the power factor, right? So the power factor is simply equals to cosine D, because right now I'm using angle, so I use cosine D. B angle minus I angle. Okay, just like that. So that will be my power angle, because when we have this this is our B, which our reference is 120. If in the polar representation is 120, and then this 0 degree. And then this current, it is lagging, because this is minus 30 degree. Okay, this is minus 30 degree. Okay, so that is actually 10 minus 30. Okay, so right now, if I want to calculate the power factor, it is the voltage angle, which is 0 minus 30, so that will be 30 degrees. So let's see what that value. So I run it. Oh, I need to show you. Run it. So you can see the power factor is that. So if I also want to print out this, I can do the same. Just copy it and see. Power angle, power factor is, and then I just use a float number, and then this backslash n, it is return. It will give the, it will write this in another row. It start a new row. Okay, so this will simply be the variable PF. See if I run that, what will happen. So now you can just write them out and say power factor is this much. Okay, so next we're going to compute for the complex power, that is S. So S equals to B times, here you can use a B times I, because the complex power should be conjugate part of I. Okay, so basically this means if I have a value here, this means I can't directly use this times this current. Instead, I need to take the conjugate of it, so that it will be 8.66 plus 5J, and then times 120. So that is my how I compute for my complex power. Okay, so a lot of students tend to forget that you have to use a conjugate of I. You directly time B times I, then that's incorrect. Okay, so if I do that, and then the other thing I can do is I can also print this out. Okay. So this will be my complex power is okay. So if I run that, you can see that this is my complex power, and then it gives me the complex power value. But here, this is you can see that one thing you need to know is, let me just clear this drawing here. So one thing that you need to notice is when we have this simply let it print out S, it will only print out the real part of it. So if we want to print out the magnitude of S, we should do absolute value of S, okay? So that will be P square plus Q square, okay? So when we do that, we will have ABS. So this way, you can see that when we print them out, they are the magnitude of the S value, okay? If you only just say print out S, because this is a full number, it's only going to print out the real part of it. So the real power part, you can also compute it by, say, power equals to S times power factor. This should give us the same value. If we run it, you'll see that sorry about that. This should be ABS. So that's the magnitude of S times power factor. Run that. So you can see that when you use S times power factor, it gives me the real part of it. That's the real power. Okay. So if I want to compute for the reactive power Q, that should equals to ABS. That's the magnitude, the RMS value of S, basically, times SQRT 1 minus P square. Okay. So that should give us the Q value. So let me run that. So you can see that the Q value is basically, let me see where I must have made a mistake here. Oh, sorry about that. Should have used it. What am I thinking? Okay, so it should be SQRT 1 minus P, this should be ABS S square. That's that. So this is how we compute for the reactive power. Let me run that. You can see this is reactive power magnitude is equals to that. And then the other way of computing for reactive power is ABS S times SQRT for 1 minus power factor square. Okay, so this would be the way I can also do, because the power factor is 0.866. So 1 minus that, and then the square root, the square of power factor, and take the square root. That would be the sine part of this angle, and then you times this magnitude of the complex power. You can also get Q. So let's run it. You can see that it can also give me the value of Q. So to summarize this, if you want to compute for the real power, then what you can do is that you can first compute the complex power, and then use the complex power times the power factor, which is computed by the angle difference between the voltage and the current. And then you take the cosine of it, that will be my power factor, okay? So you use the magnitude of this complex power times this, then it will be the real power, okay? So that will be this part. And then if you use this, the magnitude of S times square root 1 minus the power factor square, then that will also give you this reactive power. Or you can directly use the magnitude of the complex power, the square root of the square of it, minus the square of real power, and take the square root of that. That's another way of doing that. So the last way to do that is take the real part of S. So that will be my P. So this should give me the same value. And then I take the imaginary part of S. So that should give me the Q. So there's a number of ways you can do it. Either way will work. You can see that this gave me basically the same value. So in total, there are 3 ways that you can use for compute for the reactive power. And this is the ways you can compute for the real power. Okay, this is how you do the complex power. So the next thing that we are going to do is to compute a Z. So Z equals to V divided by I. Okay, so if I run that, you can see that, let me clear this up a little bit. Okay, this is look cleaner. So now next, let me start a new section. Section break. Okay, so this will be the section break. So here we will just compute for load impedance. Okay, and then this one just compute for real power and reactive power. Okay, so when we compute for load impedance here, you can see we can simply use that. And then there are a couple of things. Let me just make it faster. I don't want to type in them one by one. It's just too slow. So you can print it out again. So you can see that the impedance actually have two parts as well. This is the resistance, and this part is either inductive or capacitive. If this is positive, then this load is inductive. If this is negative, then this load is capacitive. So we can run this. You can see that the load impedance is simply this value, right? So the resistance equals the real part of Z, and then this reactive part of it is reactance. So there's another thing we can do here. Actually, if our X load is greater than 0, then what will happen? Then L, then our, let me just copy that. Then our impedance basically equals to R plus J omega L. So the load is the inductive. So if that's the case, then we can compute for L simply equals to X load divided by omega, because you can see that here we have in this part J omega L equals to J X load. Okay. Therefore, L equals to X load divided by this. Okay. Okay. So then we can have that part, and then else if X load is smaller than 0, then what will happen? If that's the case, then our impedance basically is capacitive. So that means my X load equals to 1 divided by J omega C. Okay, so that means that my C will equals to 1 divided by X load times W. And then that way I know that when this is greater than 0, it is inductive, and then I can compute for the inductance. And then I can, if this is smaller than 0, I know it's a capacitive. So I can use this value, because here, if I show you how this is the case, because 1 over J omega C equals to X load. So this is J. So C equals to 1 divided by X load. Okay. So this is how this is computed. Okay. And then this is how this is computed. Okay. Then if we do that, we'll see that when I run it, I can know that, okay, because here my angle is minus, meaning in this particular case that this is my voltage. This is the voltage 120, okay? And then this is a current, which is 10 and minus 30. So my current I is lagging my voltage by 30 degrees. So this is the inductive load, right? So then you can see that when I do the computation, it shows me that here the load is inductive. So we can just print them out like this. And then I can print out this. So basically this says load is capacitive, and then I print out the R and the C. And then else, if this is equal 0, then it's simply B, the load is resistive. So if the load is resistive, I simply plot out the load is resistive and plot out R. So let's do a testing. So if I have the current is leading, see this current is leading by 30 degrees. So that will be 10, and then I have 30 degrees. So this is a plus 30, okay? So if that's the case, what will happen? If this is the case, then when I run it again, I just run the whole thing again. So you can see that load is capacitive, and then R is this value, and then the capacitance is simply B, this C, right? So if I took this value again, this current right here, I change it to 0, then it should be right here. This is 10 and 0. So then the load should be resistive. Let's see if that's the case. Okay. So I change this value to 0 and then run everything again. Indeed, you can see Z equals to that. The load impedance is this much, and then this load is resistive. Okay. So the load is resistive, and then the impedance is this much. Oh, I shouldn't put the F here. This will be ohm. Okay, so run that again. Load is resistive, and then R is this much. Okay, so again, if we do this as minus this as minus 30, so this is basically a knob that I can play with. Okay, this is a knob to play with. Okay, so I've changed this to minus, then this will be behind the voltage, and this should be a inductive load. If I run that and then go back, and then this is saying load is inductive. So in this video, I just introduced to you how to calculate the complex power here, and then compute for the load impedance if the voltage and current is given. So in our next video, I'm going to introduce the second way for computing the complex power, where that we gave you the impedance and then let you compute for the complex power and current. Thanks for watching. I'll see you next time.